All right. So can you see the screen? I hope you can.
Yes.
Thank you. So yeah, in the last lecture we finished the thing about divide and conquer, and today I'm going to start the new topic of dynamic programming. Okay, so till now we have seen these two methods. Like first was greedy, which seemed like quite natural. So my desk is moving. Hope that's not too distracting. So greedy was like more natural way of looking at the solution. But the problem was that, I mean, it's not easy to prove that a greedy strategy is correct. And actually, it's not even sometimes it might not even be true. So many problems cannot be solved using greedy. And we'll see an example. The second technique that we saw was divide and conquer, which was again good, but the problem was that we had discussed in the first lecture when we were doing divide and conquer that usually the improvement is within polynomial space. Within like polynomial time. Here I mean space meaning the polynomial time space. That from n square you go to n log n or something like that. So yeah, so that is generally the case. But how do we go? The question can be how do we go from exponential to polynomial? And sometimes then this technique of dynamic programming comes to help. So today we'll see it with an example. So, but let's just say what we are trying to do, and then we'll formalize it slightly more later. First, we'll see an example today. So this is actually kind of opposite of greedy. You don't make local choices. You are trying to build a global thing. Greedy and borrows similar in spirit, with some idea from divide and conquer. And what ideas it borrows? So it explores the space of all solutions, right? By decomposing the problem into subproblems. And then finding solution to the subproblem to smaller subproblems, build a solution, build solutions to larger and larger problems, subproblems. Till finally you hit the whole instance, right? Good. So this way it might look like that this is like very close to brute force. That basically you are going through the whole solution space and so on, right? But again, it goes through the whole solution space carefully And this solution space can be exponential, right? So we'll see an example. And it does so, goes through the solution space without considering them explicitly. So all the points in the solution space are not considered explicitly. So that is why, even though the solution space can be exponential, this strategy will work in polynomial. So as I was saying, we'll start with an example, which is going to be weighted intervals scheduling. Okay. And if you remember interval scheduling, the input was n intervals, whatever, 1 to n. And for each of them, we had a start time, finish time. So and now we have another thing called VI, which is value. Yeah. And this is for all I we are given. And what is the question that we have to answer? Or the task? To find S subset of 1 to n such that, let's call it V of S is equal to summation I belonging to S Vi is maximum. Subset of maximum and all the intervals in S are disjoint. Okay. So we had seen interval scheduling earlier, and this is weighted interval scheduling. So this is a generalization of the interval scheduling problem. Why is this a generalization? Can someone tell?
So there the VI was assumed to be same for means all the requests which were there in the original thread.
Yeah. So basically, what we can say is that this is a generalization of interval scheduling, because in interval scheduling, put all VIs same, or let's say 1. Okay. Good. So this is a more general problem, so might be considerably harder. And what was the approach that we had? The greedy approach. What was the greedy algorithm? Does anyone remember?
We chose the one which finishes first.
Choose the one which finishes first. Thank you. So can someone come up with a counterexample why this one will not work? Like, just a very small one.
So we can have only two intervals where the one which finishes first is of lesser value and intersects with the second one.
Yeah. So just like to make it slightly more this thing, why do I have? So you have this interval. Let's say this is first interval. Then you have second. In fact, you can have a third also, just to make the example like slightly more non-trivial. It is still trivial, but still. So let's say v1 is equal to 1, v2 is equal to 4, and v3 is equal to 1. Right? Okay. So in this case, the greedy algorithm will choose this one and this one, and the total value will be 2. But the optimum solution is this one. And you can go and see that actually no greedy strategy works for this problem. Okay. For each of them, you will be able to find a counterexample. Right. Okay, so then what how do we go about it? How do we end up solving this problem, right? Okay, so there is one, again, like earlier, let's give more structure to the problem itself. So first, let's say that the intervals are ordered, like we have ordered here in the same way. So some assumptions which are not very weird assumptions. So the intervals are ordered by finishing time, let's say. That is, if I is less than j, implies fi is less than or equal to fj. And I mean, we can assume that all the finishing times and starting times are different. That should not be a problem. Okay, cool. So this is one assumption that we have already given the ordered set. If otherwise, we can just order it, right? Good. Now there is another thing we would want to compute, which is quite useful, because suppose you want to schedule an interval. Suppose you are going from left to right. There is an interval like this, and if you want to schedule this, then you cannot schedule anything before this that comes and intersect. So you want the interval that immediately before this that does not intersect. So let's call this. So I'm going to write that definition. So let's call this Pj is I less than j, such that I is the largest index, or largest I less than j, such index not intersecting with j. Okay. So let's just see this with an example, like a quick example. Again, I'm drawing x-axis for some reason. Sorry, y-axis. Okay, so suppose you have 6 intervals, 2, 3, 4, 5, 6. So first interval goes, let's say like this. Let's say v1 is equal to 2. Whatever. We don't really need the values right now, but it's okay. We can put them also. v2 is equal to 4. v3 is equal to 4. So v4 is equal to 7. v5 is equal to 2. I'm just copying the examples from the book actually. And v6 is equal to 1, let's say, right? And now I want to find this p value, the previous interval sort of value. So, and we'll put pj is equal to 0 if no such interval exists. If all I less than j intersect j. Okay. So what is value of p1? What is the value of p1? I mean, so what I've written is not very formal, in mathematical terms, because I'm doing some self-referencing there, but I hope you get the idea. I mean, the definition of pj. So I should have written largest index I such that I is less than j and I does not intersect with j, but you get the idea. So what is the value of p1?
0.
0. What is the value of p2? Why is 0? Because there is no interval, there is no I less than 1 for which it does not. Actually, there is no I less than 1.
P2 is also 0.
What about P3?
1.
1.
P4?
0.
0.
So,
Yeah, 0. P5?
3.
3.
3. P6?
3.
3.
Right. So this is the thing that for an interval, we look at, which was the interval which finished right before this, right? The largest index that finishes before this. Okay, good. Now, why are we doing this? It will become apparent in just a moment. Okay. So now we consider an optimum solution, O. Okay. Now look at the last interval, let's say. N, right? Now there can be two cases. If N belongs to O, right? Then what can we say? So if N belongs to O, then can we say something about the intervals which come before N, whether they'll belong to O or we have defined this Pn and so on? That whether they'll be in the solution or not in the solution. Can we say something?
All I less than equal to Pn will like all I greater than equal to greater than Pn will not be in the solution except n.
Exactly. So any I belonging to, let's say for all I belonging to Pn to Pn plus 1, whatever, n minus 1, I is not in O, right? This we can say. Good. Can we say something else also? There's another thing actually which is quite nice that we can conclude from this. What about the solution from, so if we look at the sub-problem, one to Pn minus 1, let's say. No, shouldn't it be Pn plus 1? Nobody's pointing it out because Pn is disjoint. Should be Pn plus 1, right? Can someone confirm if I'm not making a mistake?
Yes, sir. It should be Pn plus 1.
Okay. So if we look at the subproblem now, 1 to Pn, can we say something like, can we relate the solution of this subproblem with O? So let's say that, the best solution for this is O prime. Then can we say something about O prime and O? Let's say that, yeah, let's say for now that unique optimum is there, just for, yeah. Tell me.
O is equal to O prime union n.
O, right now we are in a case, yeah, but if N is in O, then yes, we can say that. If we are in this case, then we can say that actually O is equal to O prime union N, right? Why? Because otherwise you can just substitute this O prime. You can do that exchange argument that if O prime was not in O, then you replace whatever was in O. O must have a subset of this, but you replace that subset with O prime, and then you get a better solution. So this is a better solution than any other. And whatever O has is a subset of this, is a disjoint subset of this, because everything else intersects with N, right? So this is the case when N is in O, then we can say that O is actually the optimum solution of O prime union N. Is there any question about that? Or we can say that O contains an optimum solution for whatever 1, 2, 3. Okay. So this case is fine. Now case 2, let's look at that. What is case 2? That N does not belong to O. Then what is O? Can we go to any smaller subproblem?
1 to n minus 1.
Exactly. So O is the optimum solution for, or an optimum solution if suppose you are not like, you don't want to go for unique solution for 1, 2, and minus 1, right? Good. So, and again, the same thing is there, that, okay, since N does not belong to O, if, again, exchange argument, that if O is not an optimum or optimum solution for 1 to n minus 1, then 1 to n minus 1 has a better solution, which is better than O, and that will violate the optimality of O, like, that you can do. I mean, this is not very hard. Okay, good. So now we have this strategy sort of, that what do we do for finding the optimum? Right? For 1 to n, if we can find the optimum, if we have the optimum for j belonging to 1 to n minus 1, that is all the smaller j, then we can find optimum for m. Right? Because here also we wanted something smaller, and then we can compare these two cases, right? So let's see how we do that. So let's first again put some notations, that let's say OJ be the optimum, or be an optimum. Again, I keep using the optimum. Optimum solution for, let's say, 1 to j, right? And opt of j is value of OJ. That is, let's say, value of OJ. I belongs to OJ, Vi. Right. So that is opt j. And we want to initialize things, so we can say that O0 is equal to empty set, and opt 0 is equal to 0. Right? So this is the initialization. Good. And what do we want? We want to compute ON, right? That is our target. Good. And also maybe opt n. This is not opt O. Yeah. Okay, good. So now from the previous thing, what do we have? Meaning discussion. I'm just going to write the same thing that we discussed notationally, right? That for all j belonging to 0, 1, 2, whatever, n minus 1. So we discussed that with n, but that is true for every j, right? And what is that? That either j belongs to OJ We are generalizing that to now any j, right? And if j belongs to oj, then what did we have? That opt j is equal to vj plus opt of pj, right? And or j does not belong to oj. And then what do we have? Opt j is equal to, what will be the value in this notation?
Opt of j minus 1.
Opt of j minus 1. So is like these two are clear or not? So this is just that okay, if j is in oj, then of course nothing. So oj contains vj. Of course, the value will contain vj, and nothing from pj plus 1 to again j minus 1 can come in the solution. So the opt of pj will be in the solution, in the optimum solution for j. So it's the same logic. I'm just writing that notationally that I said earlier. Right? Any questions till now? Please ask. Okay, no?
Sir, could you just explain what OJ is? I just got confused.
Set to be just 1 to j, you don't go till n. Okay?
Got it. Got it.
This subset of 1 to j that is disjoint and has maximum weight, has maximum value.
Okay, got it. Thank you.
Any other question? Okay, so I'll go ahead. Good. So now, but these two are exhaustive cases, right? That, either j belongs to oj or j does not belong to oj. This is exhaustive. And what does that mean? If it is exhaustive, that now we can just write one thing using, the max, right? That this implies that opt of j is actually max of these two quantities, vj plus opt of pj, comma, opt of j minus 1, right? Good. And from this, actually, we can even decide whether j belongs to the optimum solution or not. So this is opt of j, this is the value. And suppose we want to find the solution. Suppose we want to decide whether j belongs to oj, right? And for that, we can just say that request j belongs to an optimum solution oj for the set 1 to j, right? If and only if, what conditions should satisfy? When does it belong? When the max, in the max, what happens? So we want to derive it from here.
Opt
Yeah.
of j must be equal to vj plus opt of pj.
Opt of
J must be equal to vj plus opt of pj.
yes, exactly. So let's just say that vj plus opt of pj. So exactly right, but I'm just saying is greater than or equal to opt of j minus 1, right? exactly what you said, that it should be equal to the first value, and the first value, it will be equal to the first value when the first value is at least the second value, right? Okay, good. So now this also gives us a way to compute the optimum, right? Because now this is like a recursive procedure that we can do, because it only uses the smaller values. Pj is also smaller, and j minus 1 is also smaller, right? So suppose we have like, you know, sorted the intervals which we have assumed already by fi, and calculated also pj for all j. Okay. Right. Then this gives us a recursive procedure. Recursive procedure to compute what? Opt j, right? So let's write this procedure. Compute opt, let's say j, and this is just basically we'll look at this, right? This, that formula basically gives. So you just write that basically, and that's the algorithm. What does it say? If j is equal to 0, then return 0. Else, return max of these two values, right? Pj plus compute max, compute opt of Pj, comma, compute opt of Pj minus 1. Right? Sorry, not Pj minus 1, J minus 1. So I have just written this formula below, this formula that we have, right? And that is what this algorithm does. So is the algorithm clear? It is just a recursive algorithm, a simple recursive algorithm. And how can we prove the correctness of this algorithm? How can we show the correctness?
Sir, I think we can use strong induction on this. Like, let's.
Yeah, we can use induction like that for j equal to 0. Like, we have that opt of 0 is equal to 0, and algorithm results 0. Now suppose algorithm computes correctly for all j less than or equal to k, and now for k plus 1, or let's say j strictly less than k, just to, so that let's use the same terminology, so that for all I less than j, and now we want to compute for j. What do we want to compute? And for j, what do we want to do? We want to compute this, compute opt j returns the value this one, which is correct because we have shown that it is equal to this, opt of j. So yeah, after you have shown this, then the proof of correctness is just one line, right? Opt of j uses compute of j minus pj and compute of j minus 1, which we have that by induction they are correct. And hence the value of compute opt is correct, right? Because of the formula that we had. Opt of j is equal to opt of j. What does it mean by correct? That this is equal to opt of j minus 1, and this is equal to opt of pj, right? And so finally you get that compute opt is equal to opt of j, and this is the correctness. Any questions about the correctness? So in the correctness, what do we need to show? That the algorithm outputs the opt. That's what we need to show. So the by induction, the smaller calls output the opt, and hence by the formula, the algorithm outputs the opt. Right? Good. So that is fine. But what about the running time of this algorithm? How many calls is it generating? Can someone say that how many recursive calls it can generate in a bad case?
Sir, in a bad case, I think for each j there can be j minus 1 calls. Like if tj equals to j minus 1, then again j minus 1 will call for j minus 2. In such a case, there will be j minus 1 cases.
Yes, but those are, you are saying that for each j there can be j minus 1 calls. Actually, there can be more, I'm thinking. Yeah, there can be more, right? So suppose you have this. So actually not j minus 1. Actually, it can be much larger. In fact, for every problem, so you have suppose something like this. That suppose the intervals go like this. So let's say 1, 2, 3, 4, 5, 6. Okay, so they are not disjoint. So P of I, let's say, is equal to I minus 2, right? And so suppose you have this call for 6. So let's just say C6, which calls C5 and calls C4. Then this calls C4 and this calls C3. This calls C3. This calls C2 and so on, right? C3, C2. So, I mean, this is generating a lot of calls, right? C1, C2, and similarly here also 2, here also 2, and so on. So it can go exponential. But all these calls seem quite wasteful, right? Why?
A lot of values are repeated, like C4 is called twice, C3 is computed twice.
Same value is computed many times. Okay. So what if we compute it once and store for later? Okay. And this is what is the technique called memoization. That you make a memo of it, that okay, I have computed it. If I need this value in future, then other parts of the algorithm, other recursive calls of the algorithm can use it. Okay, good. So the idea is that compute the value for smaller subproblems. And store it globally, so that future recursive calls can access it. If calls are not needed, actually. Yes, so this is the idea, right? Good. So let's now design the algorithm using this idea. So what is, let's call this algorithm whatever, mComputeOpt, as it says in the book. Right? And now what do you want to do? If j is equal to 0, then whatever the base case returns 0. Now else if, so let's say mj is where you will be storing for opt of j, right? So else if mj is not empty, if you have already stored something, then return mj. So first you check whether you have already computed, else you compute it. And what is it going to be? Again, the same thing, max of vi plus mComputeOpt p of I or j, right? P of j, comma, mComputeOpt of j minus 1, right? And that's it. Return, you compute it, then return. Right? And you have stored it here also. And that's it. Okay. So now we want to do the analysis of this. We hope that this will be faster. Right? The correctness is exactly the same. But what about running time? So each call, if no recursion happens, then takes order one time. Why? Then we are just looking at the value of mj and returning it, right? So basically, we need to bound the number of recursive calls. And how can we bound the number of recursive calls? It's not very apparent, like, that we can directly bound. But still, can somebody suggest something? That this is an algorithm. How here we can bound the number of recursive calls that are happening here. So recursive calls are happening only if the algorithm goes here in this else part, right? And when does the algorithm go here in the else part? If mj is not empty, right? So any ideas how we can now do something or say something? Also, every time it goes into the recursive call, one MJ gets filled. Since it is empty, this MJ gets filled.
And
Okay,
we can have at most J recursive calls then, means because all the values will get saved.
Exactly. So we put a measure approach that how are we making progress, measure of progress. And measure of progress is how many values, MJ values, are stored, right? At any point. And the thing is that any recursive call increases this value, increases the measure by 1. And the maximum value of the measure is n or j, whatever. If we want to solve for the whole problem, then it is n, right? Because you will compute for n. So that is what gives the number of recursive calls less than or equal to n. So running time is order n. Order n after we are given the sorted list and we are given the values of Pn. And Pj for all j. So is the algorithm clear? Is the running time analysis clear? So what did we do? We said that, okay, we don't know how we bound the number of recursive calls, but how do we bound the number of recursive calls? We say that every time a recursive call happens, this value, one more value gets added, which was empty earlier. And there are at most n values that can be added. There are at most n values of mj. So there can be at most n recursive calls, which are here, right? In this step. And recursive calls happen only in this step, not in this step, and this step takes order 1 time. Okay, good. But there is one more small problem, that is that we have just found oj or opt of j or opt of n, didn't find on. So how can we find on?
For each n, we can store another array list which stores the value of the index that the last index in the ON.
Yes. So exactly in the similar way. Same way, using the lemma. And what was the lemma? The lemma said that we can decide for an OJ. Where was this? Request J belongs to the solution if this happens. If Vj plus opt J is opt of J minus 1. So now we have already filled this opt Mj wala array. So we have already computed Mj. And now we can recursively again compute opt or OJ, right? How? So this is the algorithm. Find solution for J. So you will, call find solution N. Right? And find solution N. If J is 0, then it outputs nothing. and then it just uses that whatever we had in the lemma, that okay, what is the value of m for this, and if this value is greater than or equal to this value, then it outputs j together with the result of find solution of pj. So it calls find solution of pj, and again it can store that find solution thing, right, and output the result of find solution j minus 1. Right. Actually, here we don't even need to do that. Here there is only one recursive call. There are no two recursive calls. So we can just find solution pj we can call, and then find solution j minus 1 we can call. Otherwise, and then there can be at most n recursive calls, because every time the size decreases, size is decreasing. Every recursive call is on lesser value. Call, or there is just one recursive call, let's say that, to get find solution j, there is only one recursive call, and that is on less value than j, for I less than j, some I. This I can be either pj or it can be j minus 1, depending on which case it is. And how do we determine the cases? We determine the cases from the table that we have made, the array that we have made of mj, right? And since it is less than that, there are at most n recursive calls. So time is order n, given the above array, given mj for all j belonging to 1 to n. Okay. So this way we can find the solution also. This was not very hard, but just to that we are not just finding the optimum value, we are also finding the optimum solution. Okay. So any question about this? This or anything now. So basically we have finished the lecture. So is there any question about the algorithm, that okay, how does the algorithm work and so on? Or how are we analyzing the algorithm? We analyze the algorithm using this measure of progress, that the algorithm is making progress, and how many times such thing can happen, and then we bounded that, and then we had the whole running time bound for the algorithm. Right. Okay, so good. No other questions?
Sir, how do we compute PJs? I mean, how do we compute PJ?
Oh, PJ. So that initially you can just go through the thing exactly once. So what do? So you go from here. So for one, which guy it can be PJ for? So you're going to the right in one pass, and so for one, you calculate PJ. For the second one, you want to calculate PJ. So you figure out where did the last interval. It can be done in n square for sure. I'm thinking whether it can be done in less. N square you are fine with, right?
Yeah, n square is all right.
Yeah, n square I'm fine. So yeah, maybe it will take n square, but that is still okay, I guess. Because anyway, the sorting will take order n log n. So this PJ calculation, at least the naive way I can think of is n square. Maybe there can be a faster way. And if somebody comes up with that, let me know. But maybe we have to scan through all. Last finishing running time. Yeah, if we have both the sorted arrays, Si and Fi, then we can find it, I think, in linear time. But I'll have to think about it. So right now, I did not really think about it, that how we can compute, because this is not going to be exponential, definitely. It is still going to be polynomial. It is definitely n square, but maybe it can be done faster, given the sorted arrays for both Si and Fi.
Okay, sir.
Only from Fi, I'm not sure. Only from Fi, I think it will take order n square. But if we have both the sorted things, Si and Fi, then I guess we can do. But yeah, I'll have to think about it. maybe you can also think about it.
Okay, sir.
Any other question? Okay, good then. So see you guys next week. And yeah, thank you for coming.